Okay, let's continue our review for the Unit 2 exam. And so our next lesson is lesson number 15 on waves in motion. Remember to read the lesson objectives because that's going to help prepare you for the exam. And then read out of your textbook chapter 19 and then sections 3, 4, 5, 6, 7, and 8. So you ought to know the two types of waves. Know the difference between an electromagnetic wave and what a mechanical wave is. And you ought to be able to give me examples. So give me at least 2 or 3 examples of electromagnetic waves. So you could say radio, infrared, visible light, ultraviolet, X-rays, and gamma rays. And then be able to give me 2 or 3 different examples of mechanical waves. So that would be like earthquake waves, water waves, and then also sound waves. So these are all types of mechanical waves. Know the definitions of them, and you should also know that mechanical waves have to have something to carry it. So the rock going up and down carries the earthquake waves. The sound is carried by the air molecules. Okay, but electromagnetic waves, on the other hand, they do not require anything to carry them. So they can go right through outer space. Okay, the next thing is know the difference between a longitudinal wave and a transverse wave. So could you make a picture of a transverse wave? Could you make a picture of a longitudinal wave? All sound waves are going to be one of these types of waves. And all light waves are going to be one of these types of waves. So you might want to go back in your notes and figure out which one's which. So light waves are an example of blank waves. Sound waves are an example of blank waves. Now you can do both of them with the slinky. And then also you have surface waves. So know what a surface wave is. Okay, then you have waves that travel. So if you took a slinky and gave it one shot, you're going to have one wave traveling down the slinky. So it's traveling. But in order to have a standing wave, you need to have a wave that is traveling in this direction, and then it's going to bounce off of something, and then it's going to go in the opposite direction. So the wave initially is going this way, and then it ricochets and it goes backwards. If you are making it go at just the right frequency, you can generate a standing wave. And so, for example, if this thing was turned into a standing wave, then it would look like that. So this would be 3 standing waves. It all depends on the frequency. So if you're doing it at a slow frequency, then you only get 1 standing wave. But if you start to increase it at a certain frequency, you'll get 2 standing waves. Okay, then you should know what does frequency have to do with light. So the frequency of the light tells you the type of light it is. And you should be able to make the electromagnetic spectrum. So if you start over here with the radio waves, and then next to it we're going to put the infrared. Now you should also know the various parts of the visible part of the spectrum. So the Roy G. Biv. But remember, you start with the red on this side. So Roy, and then G, and then Biv. So that's the visible part. And then on the other side of that is going to be the ultraviolet, and then the X-rays, and then the gamma rays. Be able to make that picture. Also, notice that on this side over here is the small frequencies, And then on this side over here is the big frequencies. As far as sound is concerned, the frequency of sound is going to be the pitch. Okay, then amplitude for light tells you how bright the light is. Amplitude for sound is going to tell you how loud the sound is. Okay, then we introduced a new concept called the wavelength. So if I was to give you a wave, I could give you a ruler and say measure the wavelength of that wave. And so it's going to be wherever the wave is at its crest to a crest. Or it could be from a trough to a trough, or it could be from here over to here. So there's multiple ways of measuring the wavelength, and it's going to be in meters. So if you measure it in centimeters, make sure and convert it to meters, and then that would be the official wavelength of the wave. And so I'm not going to ask you to measure the wavelength of a sound wave, but I could ask you to measure the wavelength of a transverse wave, like this. Then you should know the range of hearing of a human. So humans can detect frequencies from 20 hertz to 20,000 hertz. Make sure and know that for the exam. Okay, then I could also ask you to tell me what do the atoms do in a solid that produces a longitudinal wave. So how do the atoms physically interact with each other that transmits the wave? I could also ask you to tell me how do the atoms react to a transverse wave. I could also ask you explain how a sound wave moves through the air. So these would all be really good essay questions. Okay, then the speed of waves. Now this is very important. Mechanical waves have different speeds. So the speed of a mechanical wave is going to depend on what it is traveling through. So you'll notice in that chart there that the speed of sound in air is 340 meters per second. But you see that it changes speed in water and glass and steel. Also notice it's going to depend on temperature, and it's also going to depend on humidity. So that as the temperature goes up, so does the speed of sound. As the humidity goes up, so does the speed of sound. But when it comes to light waves, electromagnetic waves, they always travel at the speed of light. So if I was to say on the exam, which is faster, a gamma ray or a radio wave, don't be messed up. They travel at the same speed. So all of these are going to travel at the same speed. So what's the relationship between the frequency of a wave to its speed? It's going to be the wavelength. So if you take the wavelength of a wave and multiply it by the frequency of that wave, that will tell you the speed of that wave. So that means that on this side of the spectrum, this has the small frequencies, so it must have the large wavelengths. And then on this side over here, this has the large frequencies, so this must have the small wavelengths on that side. And it all comes down to this formula here. So in the case of light, instead of V, you would put the letter C. So C stands for the speed of light. And you should be able to do a question like this. So if I give you the wavelength, you should be able to calculate the frequency. If I give you the frequency, you should be able to calculate the wavelength. Okay, then we talked about the intensity of light. So as far as I'm concerned, so far, we haven't talked about power. Okay, power is the energy that something gives off per second, or it's the amount of energy consumed by something every second. So you don't need to know about power yet. What you do need to know is intensity is related to the brightness of the light. So that the greater the intensity, the greater the brightness of the light. And so this formula here shows how the intensity I depends on distance. So you can see from the formula that as R gets bigger, the intensity goes down. If you take a flashlight and you hold it in front of your face, it's pretty bright. But if you take the flashlight and you move it away from your face, it gets dimmer. Well, I want you to be able to go further. I want you to be able to tell me how much dimmer does it get. And so, for example, here's a question. If you get 6 times further away from a light bulb, what happens to its intensity? So don't say that it gets 6 times dimmer, because what do you have to do to the R? It's squared. So 6 times 6 is 36. So it's going to get 36 times dimmer as it gets 6 times further away from you. Okay, I would like for you to know about the decibel system. So that sound intensity is measured in decibels. And the decibels go from 0, which means that's the sound that your ear can just barely hear, and then it goes up to about 120, and then that is about as loud as your ear can take. So anything above that is going to be hurting your ears. It could possibly burst your ears, and you'd start bleeding from the ears. So I would just like for you to know what is a decibel, and then know if I gave you 5 decibels versus 50 decibels, which one's louder. So be able to tell me that. And then I'm not going to ask you any questions about earthquakes, but this measures the intensity of earthquake waves. Okay, then we talked about properties of waves. So you ought to know the definition of absorption. So what happens to light if it is absorbed? Where does the energy go when light is absorbed by water? What happens to it? You should also know what is reflection. So what's the definition of reflection? And then what's the definition of refraction? And then what's the definition of diffraction? Do not worry about the sound of the mechanical waves. So I'm interested in absorption of light, reflection of light, refraction of light, and then diffraction of light. I did want to show you that it also happens with mechanical waves, but you're not going to be tested on that. Okay, the next thing that you need to know about is the Doppler effect. So this is how, now you can say it one of 2 ways. It explains how the frequency of a wave changes as the source of the wave is moving towards you or away from you. Or you could say, how does the wavelength change as it moves towards you or away from you? And in the case of light, it's going to change color. In the case of sound, it's going to change pitch. Okay, so if something is moving towards you, its wavelength is going to get smaller. So the distance between those lines, that's going to be the wavelength. It gets smaller if it's moving towards you. Okay, if it's moving away from you, those lines are going to get further apart, so the wavelength is going to get larger. Okay, so small wavelength if it's moving towards you. Well, what does that mean about the frequency? Well, over here we said small frequency, large, or small wavelength, large frequency. So let's go ahead and put that up here. So I'm going to put a large frequency that corresponds to the small wavelength. If something is moving away from you, then what's going to happen? Okay, now these things are going to get further apart, like that. So this is if it's moving away from you. So in this case, the wavelength is going to get larger. So that means the frequency gets smaller. So be able to explain what is the Doppler effect, what does it do to frequency, what does it do to the wavelength. And then we also talked about shock waves. So what happens when the source of a wave is going to be faster than the medium that it's in? Okay, so we said, for example, that the speed of sound in air is 330 meters per second. So what happens if you go faster than that speed? So if you can travel faster than the speed in that medium, you develop shock waves. And in the case of air, that's going to be a sonic boom is going to be created. Okay, so that finishes up this lesson. Okay, so take a break. When we come back, we're going to do another lesson that's going to be on the Unit 2 exam.